I'm just waiting for 1 more minute so that, just people to join.
Sounds good. Yeah, makes sense.
Okay, we will start. Hi, everyone. Welcome to Network Seminar Series hosted by the Center for Networked Intelligence at the ACE and RBCCPS IAC. It's my pleasure to introduce today's speaker, Vaastav Anand. He will be speaking on Blueprint, a tool chain for highly reconfigurable microservices. Vaastav is a final year PhD student at Max Planck Institute for Software System, co-advised by Antoine Kaufman and Deepak Garg. His primary research focuses on improving the reliability and efficiency of cloud scale systems. We request the audience to keep your microphones silent for the duration of the talk, except while asking questions. Questions can be asked at any time during the talk, either by unmuting and speaking directly or by typing them in the chat box. Over to you, Vastav.
All right, thank you so much for the introduction. Hello, everyone, and today I will be briefly talking about Blueprint, a toolchain for generating easily changeable microservice applications. Cloud applications today are distributed. Okay, just didn't click. 1 second, sorry. Cloud applications today are distributed, and they're being increasingly developed as microservices. In a microservice architecture, each service really serves a core business component. These services are independently deployed and scaled, and the number of services is usually typically very large. So much so that if you actually plotted the dependencies of these services, it almost looks like these kind of graphs. So if you have seen a microservices talk before, this is something that you have obviously come across, and this is the kind of figure really shows the dependency of services in a system. So to see what's really going on inside, let's put our detective hats on and take a closer look at a small part of a microservice application. In a microservice application, a typical microservice serves a single capability. For example, a compose post service in a social network application would only be responsible for creating posts. These, these services are loosely coupled and are connected over the network. To orchestrate the execution of these services typically use common libraries and frameworks for adding desired features such as tracing or even implementing the communication framework as, like, let's say, gRPC. But doing research on microservice systems requires making modifications. For example, to observe the impact of queuing and queue back pressure in these systems, a researcher might want to change the specific communication framework from, let's say, gRPC to Thrift. And in another completely unrelated use case, another researcher might need to add few new features such as retries to all clients to be able to reproduce an emergent misbehavior like metastability failures. To support these changes, we have developed Blueprint. Blueprint is a compiler that allows users to easily change and modify varying aspects of a microservice application's design to generate different implementations. But at this point, you might be thinking that, well, microservices were supposed to be modular and reusable, so why do we need Blueprint? Well, to answer that question, let's take a deeper look at how the microservices applications developed today are inflexible. While all of this looks neat and tidy, in reality, an implementation of any given service ends up looking a lot like this. If you find this daunting, then don't worry. This is just one part of one service in a popular open source microservice application. The actual implementation of the whole application is far more complicated. And the reason for that complication is that the various parts comprising a microservice are tightly coupled in an application. Let's consider one of the functions as an example. This function just represents one outgoing call from the compose post service to a user service. But if you were to look at the code, you'd find it tough to find the specific outgoing call in this function. Let me help you out. Here, basically, because of the tight coupling, majority of the code in this function has nothing to do with the outgoing call. It either is part of the extra features that are being applied to the service, or the concrete choices responsible for orchestrating the code. The outgoing call, as one might suspect, is just one line of code that is buried underneath an avalanche of unrelated code that has nothing to do with the internals of the function. And this kind of coupling is pervasive in microservice systems today. And this pervasive coupling makes modifying microservices extremely time consuming and difficult. This coupling makes modifications to systems a high technical implementation effort. Some changes can really be deep in the infrastructure. For example, even just changing one service from Thrift to gRPC required more than 1,000 lines of code changes in a popular open source system. Some changes are cross-cutting. For example, a group of researchers needed to modify 1,300 lines of code to add X-ray support to one popular open source microservice system. This effort is further duplicated as these changes often need to be applied in multiple systems. And these modifications are the cornerstone of microservice research. The pattern that emerges from this is that microservice research requires the need to iteratively configure, build, and deploy variants of microservice applications that change aspects of the system design to perform their experiments. Blueprint enables configure, build, and deploy as a first-class use case for microservice researchers. Blueprint provides a set of abstractions to simplify implementing and modifying microservice applications, and a compiler to easily generate corresponding implementations of the specified applications. As a result, Blueprint leads to a 5 to 7x reduction in implementation effort, as well as a multiple orders of magnitude reduction in modification of systems. For example, reconfiguring the whole system to completely change the RPC framework from gRPC to Thrift now only requires one line of code change. While this is fun and interesting, to understand how this is actually possible, let's take a deep dive as to how Blueprint enables configure, build, deploy. Blueprint provides a set of abstractions to decompose an application into three independent orthogonal pieces that represent a unique variant of an application. Blueprint provides a microservice specific intermediate representation to represent these variants, which is then used by Blueprint's novel compiler to generate a variant implementation of a system. These generated systems can then be deployed and used for experimentation or as a target for evaluation. And researchers can iteratively perform these steps to generate as many variants as they require for carrying out their research. The key idea that enables Blueprint is that we can decouple a microservice application into three orthogonal pieces. So let's think about the application that I had shown you before. With Blueprint, the key idea is to decompose this into three pieces. First piece is the business logic. This is the core application level logic that models the end-to-end flow of executions in the system. One can imagine this to be a description of the system's functioning at a high level. For example, whether it is a social network system, or a reservation system, a food delivery system, or some other kind of application. The second piece is the scaffolding. This is the collection of backends, frameworks, and libraries that orchestrate execution. Additionally, this also includes features such as tracing, replication, timeout, retries, among any other features that you might want to add to an application. This scaffolding logic is really independent of the workflow and has no impact on the workflow itself. The third and the final piece are the binding choices, or what we call as instantiations. These provide specific implementations of components, such as what type of cache to use, choice of scaffolding, such as the choice of the particular RPC framework, and choice of deployment, as to whether the system should be deployed as Docker containers on a local machine or a Kubernetes cluster. While this is a nice key idea, it still doesn't actually give us an information or any kind of technique to be able to use this directly in microservices today. So let's see how we can convert this nice idea of three pieces into a useful abstraction. We separate these three pieces into two different input specifications. First is the workflow specification, which contains only the workflow logic. And second is the wiring specification, which contains the scaffolding and the instantiations. As you can already see, the number of nodes in the wiring spec have application and even across applications. But let's start with the workflow specification first to see what's actually going on there. The code snippet that I'm about to show you shows an example of a definition of the compose post service in the social network. This isn't the actual implementation, this is just a reduced example for this presentation. In this code snippet, the first thing you can see is, sorry, it does not work. Yeah, the first thing you see is the service interface, which defines the interface that will be publicly available to other services. This is essentially just a list of methods that other services then can call on this specific service through an HTTP REST API or through through an RPC interface. The second thing is the dependencies of each service type are passed as parameters to the constructor of this specific service instance. The dependencies of each service type, whether that be a different service type of a different component, are passed as parameters. And in this service, it receives objects of type user service and post storage service as parameters to the constructor. Finally, each function is exposed by the service, and each function that is exposed can be implemented in a few lines as it does not need to implement any of the scaffolding code. Here you can see that there's, for the same function that I'd shown before, in this situation, there is no scaffolding code available, and you can easily spot the line for getting in credentials of a user in the compose post service. That was for the workflow specification. Next, we'll talk a little bit about the wiring specification. Here, in this wiring specification, we're showing how exactly we can take we can take the services that we have defined in the workflow specification and declare instances of that specific service. Here, we're declaring instances of three different services: the user service, the post storage service, and compose post service. Once we have declared the instances, we can now then apply scaffolding to each service so that we actually get we can actually get like a full variant or a full IR representation of this variant for the system. Blueprint compiler converts these input specifications into a generated implementation of the system. The compilation takes place as follows. First, the compiler converts these input specifications to a graph-based intermediate representation of the system, where the edges between the nodes represent dependencies and the nodes itself represent instantiations, scaffolding, namespaces, as well as service definitions. Next, the compiler generates the implementation from the IR using various plugins. Each plugin is responsible for generating a specific type of artifact. The IR abstraction guarantees that these plugins can be implemented and used independently and across different applications. Here you can see the graphical representation of the specific service that we actually have defined in the previous example or in the previous slides. One thing that I would like to mention is that each variant has a unique IR representation, and each unique IR graph is not shared by any other variant of the system. The nodes in the IR graph are the components, and the components correspond to service instances, while these modifiers are essentially the same plugins that are modifying the component to add some extra behavior. An example of this extra behavior is this gRPC modifier or gRPC plugin applied to the compose post service. This modifier modifies the service such that it now runs as a gRPC server, and all clients to it must communicate with it via gRPC. To go into a little bit more detail about the edges, here are some examples of the edges. These represent the dependencies, but they also encode the specific plugins that are going to be applied to these components. This complete IR is then used by Blueprint's compiler to generate the specific system variant as configured by the workflow and the wiring specifications. So for the IR-based generation to work correctly, we impose an additional restriction on the workflow specification. No code in the workflow specification is allowed to instantiate a new component. Only Blueprint-generated code can correctly apply and configure these workflow-defined services with the configured features. And to apply features and connect instances to one another, Blueprint interposes only on the calls and connections between the components. This means that Blueprint provides the guarantee that any internal logic of the component is left unmodified and is executed as is in the generated system. To generate the modifications or generate the variant, the system generation proceeds in a hierarchical fashion. The source code generation follows the reverse topological order in the IR graph for generation. Let's consider the post example from earlier. The innermost node in the IR graph is the service definition node in the workflow specification. During the generation, this node is left unmodified. Next, in the IR graph is the Zipkin tracer node. Here, the code will be generated for the Zipkin node such that each API in the service definition is wrapped around to start distributed tracing spans and collect trace data. The final node is the RPC node for which the generated code wraps around the tracing code. This node will deserialize the requests and serialize the responses according to choice of the RPC framework, which in this case is gRPC. In addition to that, this node also generates the function for launching the server and accepting the requests. Once all the nodes are applied, the compiler then generates the run function for launching the service instance. This will generate clients to other instances so that all connections are correctly established between dependencies. The hierarchical generation also happens for the client nodes of the dependencies of an instance, and in this case, the client instantiation is also responsible for resolving ports and addresses for correct functioning of microservices. Sorry, wrong slide. Yeah, okay, so the next thing is to actually add features, we have to implement plugins or Blueprint plugins. These plugins provide specific features that can be used in the wiring specification. Each plugin provides three different things. A list of IR nodes, which are IR nodes that represent the feature or the component to be added. A generation procedure for generating the specific functionality and adding it to a specific service or an application, and a wiring spec binding, which are basically methods that can be invoked from the wiring spec to add functionality to a specific application or a service. All Blueprint features are implemented as plugins. Normally, Plugins use the core abstractions, but plugins may potentially use the functionality of other plugins to wrap around and provide more complicated versions of different plugins. Blueprint's implementation and all features and components along with the applications are implemented in 36,000 lines of code. Out of these, 4,000 lines of code represent the core compiler abstractions, while the rest are either plugin implementations or application implementations. The wiring domain specific language is essentially just a normal Go language with some restrictions of how the specification or how the wiring specification is used. We evaluated Blueprint across many dimensions. First, does Blueprint actually reduce programmer effort? Can Blueprint help researchers in doing microservice research? Are Blueprint Is Blueprint easy to extend with new features? And what is the cost of using Blueprint? What is the cost of using its abstractions? And we answer all of these questions today. First, to test if Blueprint reduces implementation effort, we implemented the 5 most popular open source systems used by researchers as Blueprint applications. And we compared the lines of code required to implement the workflow and wiring spec of the Blueprint application to the lines of code a user manually had to write to implement the original system. Here, the first column with the numbers is showing you the number of lines of code a user manually had to write to implement the original system. And these are the lines of code a user had to write to implement the Blueprint version of the same application with the same configuration. Blueprint applications require significantly less amount of manual code to implement a system, offering a 5 to 7x reduction. But Blueprint doesn't just reduce the effort to implement the systems, it also reduces modification effort. So consider the scenario where you needed to change software design choices for improving performance. To test this theory out, we changed the software choices of the Death Star bench hotel reservation system with the goal of improving performance. Changing the RPC from gRPC to thrift required one line of code. Changing the client pool size required a further one line of code change by changing basically the parameter of number of maximum clients from 512 to 4096. And then changing the granularity of the deployment from multiple microservices to a single monolith required 9 lines of code change. Blueprint makes modifications easy by restricting the amount of changes required strictly to the wiring specification, allowing the compiler to do the heavy lifting that a user might have to do manually without Blueprint. Now let's take a look as to how Blueprint actually helps researchers. To test this, we ask if Blueprint can help in researching emergent misbehaviors or emergent phenomena. To exhibit these phenomena, we generate equivalent versions of 2 open source microservice systems, Death Star Bench Hotel Reservation, referred to as DSB-HR, and Death Star Bench Social Network, referred to as DSB-SN. We reconfigure these systems to generate different variant implementations and exercise the variants with different workloads. And we showcase 2 different phenomena, metastability failures and cross-system inconsistency. We'll first talk about the metastability failures, and let's take a look at what these things are. We reconfigure the system. Okay, let me give you a little bit of a background on what a metastability failure actually is. In this situation, there's usually a system that enters a metastable state where it can't process requests any further because of a sudden increase in the amount of workload that it's processing or a degradation in the capacity that it can use to process this information. To reconfigure the systems to exhibit metastable failures, we first need a trigger, which then results in the system to suffer from the performance degradation, which continues to persist due to design choices of the application, even when the trigger is removed. There are 4 types of metastable failures, depending on the trigger and the prolonged impact on the system. There are 2 types of triggers. One, like I said, is the load amplification. which increases the workload on the system. And the second is the capacity degradation, which decreases the capacity of the system. Each of these triggers can have one of two impacts: workload amplification or capacity degradation amplification. Original variants of Death Star Bench and Death Star Bench of Hotel Reservation and Social Network do not exhibit any of these metastable failures. With Blueprint's configuration of these systems, we can elicit all four types of metastable failures. And in this figure, the hotel reservation system exhibits types 1, 2, and 3 metastable failures, whereas social network exhibits type 4 metastable failures. The latency time curve in each individual figure shows that both the average and the 99th percentile latency of requests spike when the trigger is applied, and this persists even after the trigger is removed. Only 3 lines of code changes are required to the wiring file of the or wiring specification of the respective applications to add retries and timeouts that allow the generated variants of the systems to exhibit metastability failures. So let's dive a little bit deep into like what it actually took to reproduce a type 1 metastability failure. Well, type 1 metastability failure occurs when a sudden spike in the workload overloads the system and causes more and more requests to time out. As more requests are timing out, internally, the recovery mechanism kicks in, launching duplicate requests as retries. This causes a vicious cycle of retries and timeouts, causing the system to stay overloaded. So if we go back to the wiring specification, we see that for the compose post services, for the compose post service, there are no retries and timeouts, so we can never actually see the type 1 metastability failure in that variant of the system. Adding retries and timeouts only requires 2 lines of code changes, and with these changes, we can now deploy the generated system to observe the system enter a metastable state. But at this point, we've only shown that like this problem can now be injected. To complete the full circle, we also have to show that researchers can now develop solutions as well as test out these solutions for situations like this. A potential solution for solving the type 1 metastability failure would be to add circuit breakers, which observes the failure rate of requests between a pair of services and temporarily blocks any requests for a short time period so that the system can heal and there can be some load sharing that can take place so that the load on the system can be removed. Adding circuit breakers only requires adding 1 line of code to the wiring specification to apply it to all services. This prevents load persistence and allows the system to gracefully recover, preventing the system from entering a metastable failure state. Blueprint reduces the effort required by researchers to perform these experiments and to test out these choices. And when it comes to testing out choices, Blueprint also has the ability to allow users to explore design space and to change software choices for analyzing metastability. In this situation, we can use Blueprint to try out different values of different parameters and generate different implementations of the system that have different parameter values for the maximum number of retries, different values of the workload, as well as different duration, trigger duration. So this was use case 1 where we can look into metastability failures. The second thing we can do is also look at some other phenomenon such as cross-system inconsistency. This phenomenon occurs when a read of an object immediately followed by a write of the same object returns a different value than the recently written value. This only manifests in systems which have replicated databases, as without replication, there will be no delay in the application of these updates to all replicas of the database. Blueprint only, this is something that like the original Death Star Wren systems do not have, so it can't exhibit this cross-system inconsistency. Blueprint only requires 2 lines of code changes in the wiring spec to replicate databases and elicit this specific phenomenon. In conclusion, Blueprint makes it easy to reconfigure systems to elicit desired behaviors in a given application. Now let's take a look as to how easy it is to extend Blueprint with new features. Here, adding new components requires only 10 to 50 lines of code changes for specifying a specific interface for a new component. Adding new choices for a new component require around about 200 to 400 lines of code. And extending Blueprint with new plugins requires a little bit more amount of code, as you now need to take care of all sorts of edge cases as well as provide templates that will be generated by the compiler. Usually this takes around about 300 to 700, or maybe in some cases 900 lines of code, depending on how complicated the generated code is going to look like. Finally, let's take a look as to how quickly Blueprint can actually generate these systems and the cost of using Blueprint. For most of the open source systems, Blueprint can generate a variant of the system in a matter of seconds. To conclude, Blueprint provides a toolchain to configure, build, and deploy microservice applications, leading to a 5 to 7 reduction in implementation effort, and modifications require only a few lines of code changes. You can find more info on Blueprint at our Blueprint website. And this is something that like I encourage you to try out, and I hope it's something that maybe you can use in your research from day to day. Blueprint is one project in a large part on the research on the interplay of software and hardware. We have multiple different projects and opportunities at the OS group in Max Planck Institute for Software Systems. So if you're interested in any of our projects or interested in knowing more, please feel free to reach out to us. Thank you.
Thank you for an informative talk. I'm audible, right? Yes, so we have a question from Preetham.
Yeah, hi Vastav. Interesting talk. So I wanted to check, uh, does Blueprint also have, or does it integrate well with any of the observability systems in for microservices to monitor the performance of the runtime when they're deployed?
That's a good question. Yes. So we have integrations at the moment with open telemetry libraries and systems. So for distributed tracing, we support Jaeger and Zipkin. For metrics, I think we support Prometheus. And for logs, we have like a bunch of different loggers that can be supported. So we are pretty much open telemetry compliant. And if you want to add more new things, and this is something a lot of researchers in other places are doing, or they're creating new variations or versions of these monitoring systems, they are also trying to integrate with Blueprint to test out whether their techniques work with like the applications that are in Blueprint as well. So that's something we really wanted to make sure that this actually adheres to, as well as incorporates a lot of the standardized techniques that are out there at the moment today.
So one follow-up question. So is this observability or telemetry an open loop system, or does it also feed into your the map or task graph that you have to improve if you find some performance issues or
So we
imbalances
So
specifically?
that's something that's not we're not dynamically changing systems with Blueprint at the moment. That's something that we have considered, and we're looking at it in a different project where we can take insights from measurements in the system and then update the system to have different variations of the system running that can provide performance boosts. Like for example, let's say measuring something from the workload that would be more informative in like the specific choices you might want to make in the design. That's a different ongoing project, but that's something we're looking into. It's just not part of Blueprint today.
Mhm. Thank you.
Thank you for the questions.
Are there more questions from the audience? Okay, since there are no more questions, I would like to wind up. Thank you again, Vaastav, for an interesting talk. Thanks everyone for attending. Have a great evening.
Thank you so much for inviting me. Have a good day. Bye-bye.